In this video, we'll take a look at a third example of a hypothesis test involving a population mean. Again, this is similar to section 10.3, exercises 13 to 18 and 21 to 24. In 1985, wildlife researchers determined that Indian elephants consumed, on average, 133 kilograms of plant matter per day. A zoologist at the University of Mumbai suspects, however, that the mean daily plant matter consumption of Indian elephants has changed significantly since 1985. To test this hypothesis, the zoologist observed a random sample of 24 Indian elephants and measured their daily plant matter consumption. Here are the results in kilograms. The zoologist determined that the average daily plant matter consumption was normally distributed. Is there sufficient evidence to conclude that the mean daily plant matter consumption of Indian elephants has changed significantly since 1985? Use an alpha of 0.05 level of significance. So, we'll start with step 0, which is to summarize the information and identify the point estimate. In this study, they're comparing two different time periods. In 1985, they know that the mean daily consumption for elephants was 133 kilograms. And they're comparing that to the amount of consumption for elephants this year, currently. So this year, that mean daily consumption is not known, but they did take a sample of 24 Indian elephants, observed those elephants, and measured their average daily consumption. And from that observation, this zoologist obtained all this data. This problem is a little different because in this problem you're given the actual data, and you'll have to calculate the mean and standard deviation from that data. So one way to calculate the mean and standard deviation would be to use the formulas. These are the formulas. I won't go through using those formulas in detail in this video. For now, I'm going to calculate these using a graphing calculator. On the Casio calculator, these are the steps that you would take to calculate the mean and the standard deviation. These are the steps on the TI graphing calculator. And when you do calculate the mean and standard deviation, the sample mean comes out to 131.58 kilograms, and the standard deviation comes out to 6.30 kilograms. So the sample mean daily plant consumption of Indian elephants this year, the 131.58 kilograms, is different from the mean daily plant consumption of elephants in 1985, which was 133 kilograms. And so that seems to indicate that perhaps the mean daily consumption of Indian elephants this year has indeed changed since 1985. However, we'll need to test whether that sample mean of 131.58 is significantly different and therefore sufficient to conclude that the mean daily plant consumption of elephants has changed since 1985. So step 1 is to state the hypotheses. This hypothesis involves the population mean, and so as before, we'll use mu to represent population mean. In particular, mu is representing what is unknown in this hypothesis test. The unknown here is the population mean daily plant consumption of Indian elephants this year. The population mean is known for 1985, and the sample mean is known for this year, but what is not known is the population mean for this year. So in the description of this study, it says that the zoologist suspected that the daily consumption of Indian elephants has changed significantly since 1985. It's also stating that in the question down here. When you see that phrase has changed, in your hypothesis you'll use the not equal to symbol. It's similar to if you see the phrase different. So if you see the phrase changed or different, then you'll end up using this symbol for your alternative hypothesis. So the null hypothesis is that the population mean plant consumption of elephants this year is just the same as their mean consumption in 1985. The alternative hypothesis is that the population mean plant consumption of elephants this year is now different or changed from what it was in 1985. And for full clarity, again, I've written both of these hypotheses as sentences, but you don't need to write those sentences for a quiz or test. You just need to write those symbols. Step 2 is to verify the requirements. So the first requirement, the sample must be a random sample. In this study, they do mention that this was a random sample of elephants. The normality condition needs to be checked. And in particular, this is a pretty small sample size of 24 elephants. That's less than 30. But luckily, the description mentions that the population of plant consumption is normally distributed. And because the population is normally distributed, then that will satisfy this normality condition. As a researcher, you would need to do your own test to determine whether your sample comes from a normal distribution. And in our class, we won't get into the details of that, but as a researcher, you would need to do that. And the third requirement is to check that the trials are independent by checking this inequality. I won't go into the detail of this one for now. It's in the lecture notes, and it's very similar to the first example that we did. We'll go on to testing the hypotheses. So one approach to testing these hypotheses is the classical or the test statistic approach. And it's helpful to start by sketching the t-distribution probability curve and then use table 7 to find the cutoff values, which are t-values, and they represent the cutoffs for the regions that would be unusual outcomes for a study. Note that this is a two-tailed test because our alternative hypothesis has the not equal to. Also, alpha is 0.05, and that represents the area under both tails now. And therefore, the area under each tail is 0.025. So here's a sketch of the t-distribution. This is a two-tail test. The total area under the tails is 0.05. That means that each tail has an area of half of that, of 0.025. We'll go to table 7. And in table 7, we'll need the degrees of freedom, which in this case is 23. And we'll need the area under the right tail. And that's why it's a good idea to draw out that t-curve, because this time we're not looking for an alpha of 0.05. The t-distribution curve table only needs the area of the right tail, which in this case is 0.025. So we'll go to the table, we'll look for 23 degrees of freedom. Here's 23 degrees of freedom. And a tail area of 0.025, that's right here. We'll see where they line up. They line up at 2.069. and that's the cutoff for the right tail. We also need the cutoff for the left tail, and it's going to be the same value except negative. So the cutoff for the left tail is negative 2.069. So here's what that looks like. Now we do have the cutoffs for both tails. The next thing is to calculate the test statistic. We use this formula. Put in all the values for the population mean of the null hypothesis, our sample size, sample mean, and the sample standard deviation. And when you put those values in, the test statistic comes out to negative 1.102. So the last thing is to determine if that test statistic falls in either one of these tails. Negative 1.102 is not quite in one of these tails. It looks like it's maybe around here. So it's outside of the critical tails. And because it's outside the critical tails, that means that these studies' results are not unusual and not significant, and we would say that we do not reject the null hypothesis. So another approach is the p-value approach. So to calculate the p-value, you can use a calculator, the Casio or the TI graphing calculators. Very similar to the other examples. One difference to note now is that you want to make sure that your inequality is the not equal to when you put that in for the value of the alternative hypothesis. So same with the TI calculator, you want to make sure that your inequality is not equal to in this case. And when you do that, the p-value comes out to about 0.2818. So what's the meaning of this p-value? Well, it's 2 times the probability that a random sample of 24 elephants would have a sample mean of daily plant consumption of 131.58 kilograms or less, and a sample standard deviation of 6.30 kilograms, assuming that the null hypothesis is true. In other words, assuming that the mean daily plant consumption of elephants this year is the same as what it was in 1985. One extra part to this is when you have a two-tailed test, the p-value is 2 times this probability, which is why we want to specify this here. If you were really calculating this p-value from scratch with probabilities, you'd have to calculate this probability and then multiply it times 2. So the next thing would be then to compare your p-value to the level of significance. Our p-value in this case is 0.2818, alpha was 0.05. That means our p-value is more than alpha, and that means that our study's results are not significant, and we would not reject the null hypothesis. There's a third approach that you can do for this kind of hypothesis, which is the confidence interval approach. These approaches are good mostly for two-tailed tests, and if you're doing the confidence interval approach, you would calculate the confidence interval. The confidence is going to be 1 minus alpha, so 0.95 or 95%. You would calculate the confidence interval using these steps on the Casio or the TI-83 or 84 calculator, or you can use the formulas. And the result that you get is this interval. And you compare that to your null hypothesis. If your null hypothesis is within that interval, then you do not reject the null hypothesis. And in this case, our null hypothesis is within the interval, and so we would say that we do not reject the null hypothesis. So the conclusion is that there is not sufficient evidence to conclude that the mean daily plant consumption of elephants has changed since 1985.